Hello students, this is Professor Chalai, and in this video we'll go over ionic bond strengths and lattice energies. As always, you can follow along with our Chapter 7 workbook. By the end of this video, you should be able to describe the lattice energy in ionic compounds. Let's get started. So in our previous video, we talked about bond energies in covalent compounds, where they share electrons, and we can figure those out by drawing Lewis structures to help figure out covalent bonds and things like that. In ionic compounds, we know that bonding occurs slightly differently. In ionic compounds, we have a positively charged cation, a negatively charged anion, and they attract each other through electrostatic forces. Positive charge attracts a negative charge. And so the force between them is actually can be calculated using Coulomb's law, right? Where the Q here are the different charges. So one is a positive charge, one is a negative charge, and so the force is going to end up being negative, which means it's attractive. Whereas on the bottom, the r squared is just the distance between the two ions, or the bond distance, if you will. Okay, and so if that's Coulomb law, then the energy is very similar to that, except we're dividing by r instead of r squared. So the energy, here we'll call it the lattice energy, or lattice enthalpy, in fact, will be the two charges divided by r. So it's proportional to that. There's some other constants in there that we're not going to talk about for now. So if you want to figure out what the lattice energy between any two bonds, ionic bonds are, for example, Na plus and Cl minus, we can just use their charges and divide it by their distance, their distance between them, right? That's an estimate. Now, for the distance, we can figure that out by looking at a periodic table, right? We've talked about how the radius of the atom increases or decreases across the periodic table and how they change for the various ions. So we can just look at where the atom is in the periodic table. The bigger the atom, it means that the farther they are from each other, so R will be larger. Compare this to the case where you have two smaller atoms, then that distance will be shorter, right? Small r, large r, that depends on the size of the atoms. Okay, so some rules in trying to estimate the strengths of the attraction between the two atoms. If the charges are larger, then the energy released from breaking the bonds would be larger. Why? Because look at this equation. The top here are the two charges multiplied by each other, right? So if you have a -1 charge with a +1 charge, that comes out to be -1. Compare that to the situation where you have maybe a -2 ion with a +2 ion, that comes out to -4. So you can estimate if their distances between them are roughly the same. The second case will be 4 times stronger. 4 times stronger than the first case, right? Because the lattice enthalpy is dependent on the multiplication of the charges. So typically then, the higher your charges, the stronger your lattice enthalpy. And just so that I round out the argument, since we haven't actually talked about it, the lattice enthalpy is just the energy, the negative energy that is released when two ions come together, right? If you have a sodium ion floating around and a chloride ion just floating around, and they come together to form a solid sodium chloride, the energy that is released is the lattice enthalpy, and so typically it'll be negative. And we can see that from this equation here. One of the charge will always be negative, one will be positive. So if you multiply them together, you'll get a negative lattice enthalpy. So the more negative lattice enthalpy you get, the more energy is released when you form a bond, the stronger that bond is. On the other hand, if the radius are larger, then the energy released will be smaller, or it'll become less negative because radius is in the denominator, right? So let's use this idea to try to figure out sort of relative lattice enthalpies for various ionic compounds. So let's look at number 12. We have lithium chloride, sodium chloride, potassium chloride, and rubidium chloride. They're all chlorides. I will write them down. Lithium chloride, sodium chloride, potassium chloride, and rubidium chloride. Now, because these are ionic compounds, I'm also going to put their charges, right? These are all in the first row of the periodic table. So it'll have +1 charge, and chlorides have a negative charge. All right, so now we need to figure out their relative lattice energies, and we need to sort them in increasing magnitude. So how do we figure that out? Well, there are two things, as I mentioned, that determines the strength of the lattice enthalpy. One is the charges, and the other one are the other is the radius. In all of these cases, the charges are the same. 1 plus 1 minus 1 plus 1 minus 1. And so the charges would not affect their lattice enthalpy because they have the same charge. So now we need to look at the radius. And so to look at the radius, I would look at the periodic table, right? And I see that this is in the second row. This is in the third row. This is in the fourth row, and this is in the fifth row. And we know that as we go down the periodic table, R gets larger, right? As you go down the periodic table, R gets larger. So what do we know about R? If the atomic radius is larger, then the energy released is smaller, right? Because they're further separated, and so R is in the denominator. So as R gets larger, the energy gets weaker, so the lattice enthalpy is lower. So if we were to place these in order of increasing lattice energies, we start with the weakest one, which is rubidium chloride, RbCl. Then second weakest would be potassium chloride. Third weakest is sodium chloride. And then finally we have as the strongest lattice energy here would be lithium chloride. We didn't have to think about the radius of the chloride ion because they're all the same, which means that the R values for all of these are the same, so it wouldn't impact the lattice energy very much. All right, so now that you know how you can use these two ideas to figure out lattice energies, try to do numbers 13 and 14 on your own for me. You can pause the video, and then when you're done, just unpause and we'll go over them together. Okay. All right, so let's look at number 13. We have these compounds: calcium oxide, potassium bromide, potassium chloride, and strontium oxide. I'm going to draw them again, this time including their charge. Calcium has a 2+ charge, oxide is 2-. Potassium is a 1+, bromide is a 1-. Potassium is a 1+, chloride is a 1-, and strontium is 2+ with oxide 2-. All right, so first we look at the charges. Here we have a +2 and a -2, and here we have a +2 and a -2. Remember we talked about how in that case those will be 4 times larger than the case with -1 and +1. So we should already know these two are going to be the strongest. And then potassium bromide and potassium chloride are going to be the weakest. But we still need to order them, right? All right, so now that we sort them by charge, let's sort them by radius. If you look at your periodic table, bromine is larger than chlorine, which means bromine will have the weakest lattice energy, followed by potassium chloride. Potassium here are identical, so we don't have to worry about that. So we just said that potassium bromide then will be the weakest, followed by potassium chloride. Now let's look at the two that are strongest: calcium oxide and strontium oxide. They both have oxides, so we don't have to worry about that. Let's look at the calcium and the strontium. Calcium is in the 4th row, strontium is in the 5th row. So there's 4th row, 5th row. This means that strontium is larger radius, which means it's weaker. Calcium is a smaller radius, which means it's larger. So what we end up having then is strontium oxide followed by calcium oxide. And there is our order of increasing magnitude. See how this works? We're just using these simple ideas to figure out which ionic bond will be stronger than which. Okay, let's look at number 14. Again, if you haven't done it, try doing it by yourself first. We have lithium bromide, potassium iodide, and calcium oxide. So lithium has a +1 charge, bromide has a 1- charge. Potassium has a +1, iodide has a -1 charge. Calcium has a 2+ charge, oxide has a 2- charge. Right away we should be thinking, oh, this one is the strongest. It has a 2+ and a 2-. So now we just need to figure out which one of these two are stronger, which one is stronger than the other. Lithium is in, I'm looking at a periodic table, it's in the 2nd row. Bromine is in the 1st, 2nd, 3rd, 4th row. Potassium is in the 4th row. and iodide 1, 2, 3, 4 is in the fifth row. So in each of these cases, potassium iodide, potassium ion should be larger than the lithium ion, and the iodine ion should be larger than the bromine ion. So this would be larger R in general, which means smaller lattice enthalpy. So this is the smallest, this is the largest, which means lithium bromide should be in the middle. And so we could write that this way. Potassium iodide is smaller than lithium bromide is smaller than calcium oxide. So to reiterate, we talked about lattice enthalpy. It's the energy released, so it's usually going to be negative when you take two ions and you form a solid compound. And in the next, or rather in chapter 10, we're going to go over how exactly ionic compounds come together to form these, what we call lattices. We talked about how we can figure out the energy. It comes from Coulomb's force, where it's just the multiplication of the two charges divided by the distance between them. And so the charges are larger. I don't know what just happened. That's okay. If the charges are larger, the lattice enthalpy will be larger. But if the radius is larger, then the lattice enthalpy will be smaller because the radius is in the denominator. And then we went over some examples where we sorted our various lattice enthalpies. That will bring us to the end of this video. In our next video, we're going to briefly go over this idea of the Born-Haber cycle. We'll see you then. Bye.